In this video, we are solving a general chemistry second-order integrated rate law problem. The problem states that a graph of 1 over HI concentration versus time is linear with a slope of 1.01 times 10 to the negative 2 inverse molarity inverse seconds at a specific temperature for the decomposition of HI, where 2HI yields H2 plus I2. Our first step in solving this problem is to search the statement for clues. Our first clue is that a graph of 1 over HI versus time is linear. That indicates to us that the reaction is second order in HI, our reactant. The second clue is that the slope is 1.01 times 10 to the negative 2 inverse molarity inverse seconds. We know that our rate constant K is equal to the absolute value of our slope. Therefore, K is equal to 1.01 times 10 to the negative 2 inverse molarity inverse seconds. Finally, we also have a clue in the units of our slope, which are also the units of our rate constant, and those units, inverse molarity inverse seconds, represent a second order reaction in HI. So that confirms our first clue that this reaction is second order in HI, our reactant. So in summary, when we search the statement for clues before solving any problems, we've identified that the reaction is second order in HI, and we've also identified the rate constant as 1.01 times 10 to the negative 2 inverse molarity inverse seconds. The first problem we're going to solve is to write the rate law for this reaction. Before I write it, notice I'm going to take my rate constant K out of scientific notation and write it as 0.0101 inverse molarity inverse seconds. Since this reaction is second order in HI, the rate law is simply going to be rate equals K times HI to the second power, where the second power indicates that the reaction is second order with respect to HI. You may also see the rate laws written with a K value written out, included numerically in the rate law. In this case, our rate law would be written as rate equals 0.0101 inverse molarity inverse seconds times the concentration of HI to the second power. The next problem to solve is to determine the half-life of this reaction when the initial concentration of HI is 0.22 molarity. Since this reaction is second order, my half-life equation is T1/2 equals 1 over K times initial HI concentration. Therefore, when I plug in the values for rate constant K and initial HI concentration, I find that my half-life is 450 seconds. Since my concentration was given in two significant digits, my half-life is also written as 450 seconds, which is also two significant digits. The third problem we'll solve is determining how long it will take for the initial concentration of 0.22 molarity to decrease to 0.19 molarity. To do this, we will use the second order integrated rate law equation as shown here. However, we will need to change this equation to solve for T. The rearrangement to solve for T yields 1 over K times the quantity of 1 over HI concentration at time T and minus 1 over HI concentration initial. When I plug in the values I know for rate constant and the two different concentrations, I find that my time to reach 0.19 molarity will be 71 seconds, also written to two significant digits since both concentrations are written to two significant digits. For the fourth problem, if our HI concentration starts at 0.105 molarity, what concentration remains after 3 minutes? To solve this, we will again use the integrated rate law for the second order reaction. When we plug in the values that we know, our rate constant and our time in seconds to match the units on our rate constant, and then we add 1 over the initial HI concentration of 0.105 molarity, we find that 1 over HI at time t is equal to 11.34 inverse molarity. My units of inverse molarity tell me that I'm not at my final answer yet. To get to my final answer, I will take the inverse of 11.34, and I will find that my HI concentration at time t, which is 3 minutes, is equal to 0.0882 molarity. For my fifth and final problem here, if my HI concentration starts at 0.105 molarity, what concentration of H2 remains after 3 minutes, assuming the reaction vessel started with no products? So for this problem, I have to consider that my HI concentration at time of 3 minutes was equal to 0.0882 molarity from part 4, and therefore the quantity of HI that was consumed during this reaction was my initial concentration of 0.105 minus my concentration at time t. So I plug in 0.105 minus 0.0882, and I find that the quantity of HI consumed was 0.0168 molarity during those 3 minutes of reaction. Now, when I look at the chemical equation above, I see that for every 2 moles of HI that are consumed, I am producing 1 mole of H2. Therefore, the quantity of H2 produced after 3 minutes is going to be equal to 2 times the quantity of HI that was consumed, or 2 times 0.0168 molarity, which gives me 0.0336 molarity H2. So my total H2 produced during 3 minutes is 0.0336 molarity.